October 3, 2025. The third interstellar visitor, 3I/Atlas, blazes past Mars, and for the first time in modern space history, the world's top agencies lock down. Instead of live data dumps, there's a single blurry ESA image, a NASA no-threat press line, and total silence from China, Russia, and the rest. For Oumuamua and Borisov, data flowed non-stop. For 3I/Atlas, even expert astronomers are on the outside looking in. How long can they keep the reality of 3I/Atlas secret? And what happens if the silence cracks? The clock on institutional quiet is ticking, and with so much missing, the stakes have never been stranger. The only direct glimpse of 3I/Atlas during its Mars flyby comes from a single, barely there image taken by the ExoMars Trace Gas Orbiter's KSSS camera. Captured on October 3rd, this observation pushed the hardware to its limits. KSSS, built to photograph the Martian surface in vivid detail from just a few hundred kilometers above, was never designed to hunt for faint, fast-moving objects tens of millions of kilometers away. For this attempt, the team led by KSSS principal investigator Nick Thomas set an unusually long 5-second exposure, stacking multiple frames to tease out any sign of the interstellar visitor against a noisy background of cosmic rays and detector artifacts. The result? A composite where 3I/Atlas appears as a faint, unresolved smudge. No coma, no tail, just a white dot barely distinguishable from the noise. ESA released only a processed JPEG and a short animation, both heavily compressed and denoised. The original raw telemetry, FITS files, and calibration frames remain under wraps. Without these, independent astronomers can't verify the detection, try alternative stacking, or check for subtle artifacts that might mimic a distant comet. Thomas described the challenge as photographing something 10,000 to 100,000 times fainter than our usual targets, and confirmed that even with maximum sensitivity, the nucleus and coma were indistinguishable. The pointing logs and per-pixel calibration files, routine for planetary imaging, are missing from the public record, making it impossible to reconstruct the exact observing conditions or rule out rare anomalies. This absence of raw data leaves the community in a holding pattern. With only a smoothed, lossy image to examine, even the most careful analysis comes down to trust in the instrument team's word. For now, the ESA smudge stands as the sole direct evidence from Mars orbit and the first concrete but incomplete proof of 3I/Atlas's passage through the inner solar system. NASA's official messaging on 3I/Atlas has followed a careful script since day one. The first press release, issued within hours of confirmation, featured a looping trajectory, animation, and a prominent assurance. The comet would pass no closer than 1.8 astronomical units from Earth, about 170 million miles. The phrase, "no threat to our planet," appeared in nearly every update, echoed by the Planetary Defense Coordination Office and repeated by public affairs spokespeople across social channels. But beneath the confident language, the volume of public data has remained surprisingly thin. The Hubble Space Telescope's scheduled observation on July 21, 2025, produced a statement about a dust cocoon enveloping the nucleus, with size estimates ranging from less than a quarter mile to as much as 3.5 miles. No resolved nucleus, no direct images, just a spectral profile and a composite suggesting the object is shrouded in fine debris. NASA's summary highlighted these uncertainties while steering attention to the absence of any risk, avoiding deeper discussion of the object's physical oddities. The Perseverance rover's NavCam, meanwhile, became an unexpected flashpoint. Amateur astronomers, stacking images from the Mars surface, identified a faint diagonal stripe in the sky matching Atlas's predicted path. Forums debated whether this was a genuine detection or a motion artifact, but NASA declined to issue any formal comment. Internal technical discussions, later referenced in Slack logs, leaned toward a processing anomaly, yet no peer-reviewed analysis or public adjudication followed. Across all channels, the pattern is clear: reinforce calm, release only curated data, and sidestep ambiguous details. The result is a narrative controlled less by the science teams and more by communications officers, shaping public perception with steady reassurance and minimal technical disclosure. For a visitor as rare as 3I/Atlas, the silence between the lines speaks almost as loudly as the official words. Global coordination on 3I/Atlas, once routine for interstellar visitors, has settled into an uneasy quiet. After the initial discovery alert from the Minor Planet Center, agencies from Europe, China, India, the UAE, and Russia each issued brief statements, most within a day, some delayed by translation or internal review. But since then, the expected chorus of technical updates and shared datasets has faded to a murmur. During the first week of July, at least 3 major agencies proposed joint observation campaigns through the International Asteroid Warning Network. Instead of a unified plan, these meetings became a series of teleconference standoffs. Each group waited for another to take the lead on data release or verification, citing protocol or the need for independent confirmation. The result? No coordinated public dataset, no composite trajectory models, and little sign of cross-agency technical debate. Ordinarily, a rare object like 3I/Atlas would spark a flurry of international collaboration, shared raw frames, open Slack channels, and rapid-fire preprints. This time, most agencies defaulted to their own internal pipelines, with embargoes and proprietary periods stretching weeks beyond the usual. Technical friction played a part. Ambiguous or noisy sensor data often triggers a wait-and-see approach, with each team hoping someone else will secure a clean detection first. But cultural factors matter too. In some agencies, the risk of releasing ambiguous data, especially if it could be misinterpreted, outweighs the benefit of being first. The silence isn't absolute. Occasional updates appear in obscure bulletins or after-the-fact summary reports, often buried behind layers of institutional review. But the days when planetary scientists would debate orbital models in real time on public forums seem distant. For now, the global curtain remains drawn, with every agency watching and waiting for someone else to break the stalemate. When official channels go quiet, the human mind rarely follows suit. Ambiguity acts like a solvent, dissolving the usual boundaries between skepticism and belief. In the absence of detailed updates on 3I/Atlas, speculation has filled the vacuum, sometimes faster than facts can catch up. The playbook is familiar to anyone who watched the viral surge around Comet Elenin in 2011. Back then, a faint, unremarkable comet became the centerpiece of doomsday theories and alien visitation claims, all fueled by a lack of clear, timely information. It took months of careful, methodical explanation to restore perspective, long after the object itself had faded from view. The same pattern played out after the famous Wow signal in 1977. A single unexplained radio burst that, without follow-up or closure, became a magnet for decades of wild conjecture. Each time, the longer the silence, the more room there is for extraordinary stories to take hold. Psychologists who study uncertainty call this the ambiguity effect. When information is scarce and the stakes feel high, people naturally gravitate toward the most dramatic explanations, even when evidence is thin or absent. For agencies and scientists, this presents a dilemma. Rushing out inconclusive or noisy data risks amplifying confusion, but withholding details only deepens the sense that something is being hidden. Every day without clarity nudges the public conversation further from science and closer to speculation. In the case of 3I/Atlas, the silence isn't just an absence of facts, it's an invitation for the imagination to run wild. One scientist's voice can send ripples through an entire field, especially when the data are thin and the public is restless. Avi Loeb, chair of Harvard's astronomy department, has become that lightning rod for 3I/Atlas. While most researchers steer clear of speculation, Loeb has told reporters there's a 30 to 40% chance this object is not natural in origin, a statement that lands with force in a climate of official vagueness. He points to the hyperbolic trajectory, the ambiguous dust cocoon, and the lack of a resolved nucleus as reasons to keep the door open to unconventional explanations. Media outlets seize on the probability figure, amplifying it far beyond the original interview. Overnight, Loeb's estimate becomes a headline, sparking heated threads across social networks and science forums. For every cautious astronomer urging patience, there are now thousands of posts dissecting the odds, replaying every agency press conference for hidden clues. The result is a feedback loop. As Loeb's comments circulate, pressure mounts on data custodians to clarify what they know and what they don't. NASA's communications teams field waves of new questions, while ESA's public inbox fills with requests for raw telemetry and calibration files. Even the absence of a clear agency rebuttal is read as meaningful. In this atmosphere, one contrarian claim shifts the burden of proof, transforming official silence from a technical pause into a source of public suspicion. Outside official agency channels, a parallel universe of skywatchers and commercial operators quietly tracks objects like 3I/Atlas. Amateur astronomers, armed with backyard telescopes and open-source software, have posted claims of faint detections and even rough spectra. Most of these efforts never make it past online forums, stalled by the lack of raw agency data and the technical challenge of confirming a moving target this faint. Yet, their enthusiasm keeps the rumor mill active and sometimes uncovers details missed by professionals. Then there are the private players, space situational awareness firms and satellite operators who sweep the skies for everything from space debris to classified military launches. Their sensors, often more sensitive than public observatories, almost certainly recorded high-resolution tracks of Atlas as it crossed the inner solar system. But here, data is currency. Proprietary contracts and national security clauses keep raw measurements locked away, with only sanitized summaries or vague confirmations released to clients. Requests for access, even under Freedom of Information laws, usually hit a wall of redacted documents and generic denials. Defense agencies, too, have their own eyes on the sky, but their tracking logs are buried under layers of classification and budgetary code. The result is a patchwork of possible evidence: amateur images, commercial sensor data, and classified tracks that exists in fragments, rarely crossing into public scientific debate. For every official silence, there's a hidden stream of observation just out of reach, shaping what the world can and can't know about visitors like 3I/Atlas. Every attempt to pin down 3I/Atlas's true nature runs headlong into the limits of the available data. Start with its orbit. Normally, a comet's path through the solar system can be modeled with remarkable precision. Gravity, solar pressure, and outgassing all accounted for. But the orbital residuals for Atlas, the tiny differences between its predicted and observed positions, refuse to settle neatly into place. Early fits using standard outgassing models leave a stubborn mismatch. The comet's path drifts by arc-seconds in both direction and magnitude, sometimes pointing away from the sun when the models say it should be pulled in. The error bars are wide, and the data points are few, but the pattern is persistent enough to keep theorists up at night. Spectroscopy, the tool that cracked the secrets of Borisov and Oumuamua's chemical makeup, offers more questions than answers here. Hubble's July 21st spectra hint at an odd ratio of carbon dioxide to water, higher than most comets seen before, but the margins of error are so large they could swallow the anomaly whole. Calibration drift, background subtraction, and cosmic ray hits all muddy the signal. Some ground-based telescopes report faint hints of carbon monoxide, but the detections are just above the noise floor. No clear emission lines, no smoking gun. Radio silence is the final puzzle piece. SETI arrays and planetary radar surveys routinely sweep the sky for anything out of the ordinary, but so far, nothing from Atlas stands out. No bursts, no pings, no energetic emissions to suggest exotic processes. The surveys keep listening, but the logs are empty. In the end, the hardest evidence is a patchwork of ambiguous numbers, each one pointing in a slightly different direction, none strong enough to close the case, or to rule out stranger explanations. Every observation of 3I/Atlas must first clear a gauntlet of institutional filters before it reaches the public. When a new detection comes in, especially one flagged as ambiguous or anomalous, it enters a pipeline designed to prevent false alarms and protect sensitive sensor capabilities. Standard protocol calls for an immediate internal review, where engineers and project scientists check the raw data for calibration glitches, cosmic ray hits, or any sign of instrument error. In theory, this process should take days. In practice, it can stretch for weeks, especially if the data cross international boundaries or require consensus from multiple agencies. Embargo periods, sometimes as short as 24 hours, but often extended for high-profile objects, are meant to synchronize announcements and avoid conflicting statements. But these embargoes can also serve as a brake, holding back raw files and calibration logs until every possible artifact is ruled out. The result is a data gap, not because the observations don't exist, but because they're stuck in a verification loop, waiting for a green light that may never come if the signals remain ambiguous. Artificial intelligence now plays a central role in this process. Automated anomaly filters, used by Atlas, Pan-STARRS, and commercial tracking networks, scan for hyperbolic trajectories and unusual spectral features. But the same machine learning models that flag possible interstellar visitors are also tuned to suppress anything that looks like a processing artifact. Thresholds are set conservatively, and when an object skirts the line between signal and noise, the system often defaults to silence. Human reviewers, wary of false positives and reputational risk, can override AI flags and barrier detection until further notice. In this environment, even a genuine anomaly can be quietly downranked, its existence known only to a handful of gatekeepers. For 3I/Atlas, that means the world may never see the rawest, most puzzling data until every filter, human and algorithmic, has had its say. Not every silence is empty. Sometimes it's just beyond the range of our microphones. Modern astronomical surveys sweep the sky for radio bursts, microwave emissions, and the telltale flicker of optical beacons. Yet, the search for signals from 3I/Atlas has yielded nothing but static. This isn't just a failure of curiosity, it's a question of physics and engineering. Most of our detection tools are built to catch broad, omnidirectional transmissions or strong, repeating pulses. But if an interstellar visitor wanted to communicate or simply pass through unnoticed, it would have options that render our current methods nearly blind. Tight beam lasers, for example, can focus energy so precisely that their signal would vanish into the background a fraction of a degree off target. Even a city-sized radio array would miss a message aimed just a hair away from Earth. Spread spectrum techniques, which deliberately scatter a signal across a wide range of frequencies, can make even powerful transmissions look like random noise to conventional receivers. And quantum communication, still experimental on Earth, could in theory encrypt a message so completely that only a matched device would ever know it existed. No credible evidence points to such transmissions from 3I/Atlas. But the limits of our instruments leave a hard edge on what we can claim to know. The silence may be real, or only apparent, an artifact of the narrow window our technology opens onto a universe filled with signals we're not yet equipped to hear. Yet after the initial discovery, just one faint ESA-CASIS image from October 3rd and a brief NASA Hubble release marked the total public evidence, far less than the rapid, open sharing seen for Oumuamua and 21I/Borisov. Multiple agencies, including NASA, ESA, and their global partners, have cited technical constraints and ongoing verification as reasons for this delay, while internal teleconference logs and public statements reveal a pattern of caution and information bottlenecks. Orbital residuals and unusual carbon dioxide to water ratios remain published but unexplained. No credible radio or active emissions have been reported. As of today, raw data, sensor logs, and full spectroscopic archives are still withheld from public view. The reasons, ranging from instrument limits to institutional procedures, are documented, but the full story behind the silence remains classified. With each day of continued delay, transparency and independent review remain essential for understanding 3I/Atlas and what it might tell us about our place in the cosmos.